Ladies and gentlemen, good evening. My name is Bashir Al-Hashimi. I'm the Executive Dean of Natural Mathematical Engineering Sciences. It's my pleasure to welcome you to the Higgs lecture. The Higgs lecture was started in 2012 with a talk by Peter Higgs himself, soon after he won the Nobel Prize in Physics. And I cannot think of a better way to celebrate the 10th anniversary with another recent Nobel laureate with deep connections to King's College, Sir Roger Penrose. Thank you, Sir Roger. Professor Penrose is a world-renowned mathematician whose fascinating academic career has touched many truly diverse areas of interest, including linear algebra, the theory of tiling of surface, impossible triangles, and physics. And I must admit, as an engineer, I'm really looking forward to know a little bit more about some of the terms I have used. After a 2-year break due to the pandemic, the event tonight is hosted by the theoretical physicists from both the mathematics and physics within our faculty and MES, which is appropriate since Prof. Penrose's mathematical theories have had special significance and impact in physics, especially his work related to the theory of general relativity, black holes, and cosmology. Professor Penrose got his PhD in 1958 from Cambridge after a few years at Bedford College London, Cambridge, Princeton. He came to King's College, where he worked in the mathematics department. And clearly, we were very, very delighted for Professor Penrose to make the right decision to join us. Professor Penrose won multiple awards. To name only a few, they include the De Morgan Medal, Dirac Medal, Wolf Prize, the Order of Merit, many honorary PhDs, including in 2018 from King's, and 2020 the Nobel Prize in Physics for the discovery that a black hole formation is a robust predictions of the general theory of relativity. Professor Penrose's influence on mathematics and physics goes well beyond this topic, and in addition to the topics of research already mentioned, the huge implications of his work on twistor theory of fundamental physics still being understood. Of all his impressive list of accomplishments, let me point out one that was carried out while a postdoc at King's: the mathematical treatment of infinite distance in space and time, which helps to understand the global structure of space-times. This work, validating his discoveries on black holes, is something our graduate students learn when they are introduced to space-time diagrams, more commonly referred to as Penrose diagrams. Indeed, Sir Roger is famous for his neat presentations of complex ideas in intuitive pictures, and many of his papers include his handwritten figures, and we look forward to his talks on from KCL and black holes, singularities, to cyclic cosmology. To thank him for his talk today, we will present him shortly with a cup decorated with the theme of his talk, a Penrose diagram, which I must admit I've seen just now and it looks fantastic. A black hole in a cosmological universe made by the head of the theoretical group in the mathematics department, Professor Nadav Draker. Can I invite Professor Draker to present that little present to Professor Penrose?
So you see the singularity here.
Yeah, okay, yes, I get the point. Lovely, yes.
So Roger, I'm going to put you on the spot, and I want you to be as honest as you can. Does this represent anything like what you have drawn as a diagram?
What do I have to do? I mean, it's very nicely done, yes. I think
Nadav, I think Professor is struggling to really see the diagram he has drawn, but he's impressed.
I can see my diagram. Yes, well, my eyesight is not what it used to be. But it's also just the kind of cup I like to have my coffee in. And the one I've been using has a big chip in it, so that this will be a wonderful replacement. No,
Thank
this
you
is
so
great.
much.
Thank you so much. It's wonderful.
I can wrap it up.
Thank you. Thank you very much.
Thank you so much, Nada. Please join me in welcoming Professor Sir Penrose to the stage. Thank you.
Okay.
Shall I start?
Yes, please.
Well, I hope you can hear me. Yes, okay. I want to say something else about King's College, which started off, I should say this picture you see here is from the paper which seems to have got me a Nobel Prize eventually. It was published in 1965. I wrote the paper in 64. And let's just think now. I think the talk I gave was probably at King's College. I don't quite remember. I gave a lecture on the results, which I'll describe. But go back before that. I want to say something about this picture. It represents the collapse to a black hole. You have time going vertically up the picture, and you have these little cones, which I'll say a little bit more about later. Whoops, the picture's now somewhat not... I don't quite know what happened there. Anyway, there's a history for me which led to my understanding of this diagram, which was quite before that. This was actually in 1958. And I had been I think I'd been a year as a research fellow at St. John's College, Cambridge. And I was asked by my great friend and colleague, Dennis Sharma, from whom I had learned a lot of physics. When I was a graduate student, he sort of took me under his wing and decided he would try and convert me into a cosmologist, even though I was working in algebraic geometry. He didn't succeed in converting me from that, but on the other hand, he taught me an awful lot of physics. And I say most of the physics I had learned at that time probably came from Dennis. He was a very good friend, and he would sometimes drive. He enjoyed going to Stratford for the plays and Shakespeare plays, and I would often accompany him. He was a great proponent of the idea of Mach's principle, which told you that the inertial frames locally are dependent on the fixed stars. And he would drive very fast, sometimes around corners. And when I got slung towards the door at the side, he would say, "That's the action of the fixed stars," taking off responsibility for his driving. He actually drove pretty well, even though fast. No, we haven't got round to this picture. You see, I was at Cambridge as a research fellow at St. John's College, and this was, I think, in 1958. And Dennis had told me that there was a lecture being given at King's College London that he thought I would be interested in, and he would come to, he would drive me there. So I went to this lecture. It was given by David Finkelstein. I don't think I knew anything about him before. And he was lecturing on the singularities, well, the Schwarzschild solution, which is this oldest solution of Einstein's equation apart from flat space, which was discovered by Schwarzschild. And it describes a spherically symmetrical entity. And there is this thing called the Schwarzschild horizon. Well, it's called the Schwarzschild singularity. When you write down the equations, things go off to infinity at this certain radius. And that radius, lots of people thought, well, it's places where this thing goes wrong, and you couldn't really shrink a body too smaller than that radius. The radius is determined by the mass of the body, and pretty well all bodies would be much, much larger than that radius. But if they shrink down to that size, then sort of all hell could break loose. Something like that. Anyway, the talk that David Finkelstein gave at King's College was describing that, no, this is not a singularity. You can actually extend through it. And this was the first time I'd heard about this incredible idea. Somehow you get through this Schwarzschild singularity, as it was called. Now we call that the horizon, not the singularity. The singularity where things go crazy is at the center. And he described how you could use these other kinds of coordinates which got you through, and you could do all sorts of things with it, which I found very fascinating. However, I was rather disappointed by the fact that even though you got away from that particular singularity, you still had one in the middle. And I began to wonder whether you could prove a theorem of some sort, which showed that no matter how much you wiggle this thing, you could never get rid of the singularity. It wouldn't necessarily be in the middle, somewhere around. You couldn't get rid of that singularity. And for some reason, I thought, well, how do you prove a thing like that? And I had no idea. I in fact, had very little experience in general relativity. So what could I know? I said, well, what do I know that other people might not know? Well, the thing that I knew that perhaps other people, mostly in general relativity, wouldn't know was how to use two-component spinors, which incidentally I learned from lectures given by Dirac. I won't go into that story, but it was an interesting I certainly learned from Dirac what these things look like. And I thought, well, what happens when you take these two-component spinors and apply them to general relativity? And things worked so well that I got hooked on the subject from then on. So I want to give credit to King's College for inviting David Finkelstein to give this talk, and to Dennis to tell me to come with him to hear the talk. It was quite curious because I was playing around with combinatorial physics at that time, and he said afterwards we swapped subjects because from then on he played with combinatorial physics and I played with general relativity. So I think I got the better deal out of it because I'm not sure where the combinatorial physics, okay, lots of people do it, but I was perhaps glad not to be working on it afterwards. GR seemed to have much more to work with that seemed to be directly related to the physics of the world. Anyway, that was David Finkelstein's contribution to me, and it was King's College where I went to this talk and started me off on doing general relativity in a serious way. Okay, let me try and explain more about the details of this picture. The picture didn't have the collapsing material, which is the stuff in the bottom part of the picture. I hope I can get this pointer to work here. Can I get it to work? Yes, I can. So this stuff is, you're imagining a collapsing dust cloud or something like this. I'll talk about a dust cloud in a minute. This thing collapses, and you get inside these two horizontal lines up here. You imagine this rotated round. You have to throw away a dimension, I'm afraid, because well, it's drawn on the plane, but it represents what looks like a three-dimensional structure. It should really be four-dimensional. I'll come to that shortly. Let me just say what it was describing, this picture. It describes, well, in 1939, there was a paper written by Oppenheimer and Snyder, a student of his. Oppenheimer, that was before the war, and his work on the atomic bomb and something came afterwards, but he did work on general relativity before that. And he considered the collapse of a dust cloud. The dust cloud meant that the word dust meant that there is no pressure, and the solution was like what you see here. You have this material which has no pressure, and it's exactly spherically symmetrical. And since it's spherically symmetrical and there's no pressure, there's really nothing to stop all the particles of the dust. And so that where do they go? Well, they're all aimed towards the center, nothing to stop them. The fact that they all congeal on the center and get to an infinite density at the center is not at all surprising. So people, I think, largely didn't necessarily take this solution very seriously. They just thought, okay, it's a special feature. In fact, the crucial thing was, if you like, the spherical symmetry. The dust is not such an important factor, but it did mean that there was no pressure, and therefore one thought that might mean there's nothing to stop it. Okay, you have to fast forward to the early 60s when quasars were starting to be observed. These were they're observed in the radio signals. They weren't seen at that stage. They were observed just as radio signals, and these radio signals seem to be from very, very distant objects because of the redshift. The frequency of the waves had to be, it was taken that these things were very distant. That wasn't the only solution to that, but the most probable one. That these things were very, very distant, and they were so bright that meant they had to have a lot of material in them, and considering how much material was in these bodies and how much energy was emitted from them, they were something of the sort of scale that you get in the picture here. So it seemed to be that this was relevant. On the other hand, if you have exact spherical symmetry, then the signals wouldn't escape, and what signals would they be anyway? And you have to have irregularities to get signals coming out, or gravitational wave signals, or whatever it is, would have to be from an irregular situation. However, people were interested in this at the time, but they had no idea what would happen in a generic situation. In fact, it was even worse than that, from my point of view, because there was a paper written by two Russians, Lifshitz and Kalatnikov, and in this paper they seem to have proved that in a generic situation you would not get the singularity, so that as it collapses it would swirl around to do something complicated and then come switching out again. And I think that was the common view at the time. Anyway, John Wheeler, who I'd been working with in Princeton when I went to the US it was 1959, I think, and I was there in the US for a couple of years after that. And I learned a lot of physics from Wheeler and his company, because general relativity in that time was done in physics departments. In Britain, it was done in mathematics departments. And so I learned a lot of the physics, what happens to massive bodies and things like this, white dwarfs and neutron stars and things like that. So I knew something of the physics there. But the Russian paper seemed to suggest that when you have this kind of collapse, it just swirl around and come out again. I was a bit suspicious of the paper when I looked at it. I looked at the Russian paper. I didn't notice the mistake in it. There was a serious mistake, which was later corrected, I think, by Belinsky, who then, he and the Russians wrote a paper which came to the opposite conclusion, that singularities were generic. But that was some years later. I just didn't find the arguments that were in that paper totally convincing, so I began to think using my own sorts of arguments, which I'll give you some indication of in a moment. What I wanted to consider was a collapse like this, but where it was generic in some way. So you have to imagine wiggling this picture, and do you still get the singularity, or does the singularity disappear when you wiggle it, as the Russians had seemed to suggest? Now the key thing is this thing, see if I can point the right button here. You see this little black ring in the middle. You have to imagine again that this is one more dimension, so that what looks like a ring is actually a sphere. So you have a spherical thing, it looks like a ring here, and then you imagine a flash of light on that sphere, and there will be if you imagine a flash of light on the surface, then there will be a flash going one way and a flash going the other way. If it's curved one way, you might imagine that the concave side, there will be the light will be converging, and on the convex side, the light will be diverging. What's peculiar about a trapped surface, this is the definition I gave to it, was that the light in both directions is converging. And this is a particular feature of this space-time model, so that you will have the converging in both sides. Now, if you have such a surface, and you wiggle the solution a bit, this property will not disappear. So you will still have trapped surfaces in a generic situation. Now, why is that anything to worry about? Well, I have to explain what these little cones are. You may see little cones in the picture. These little cones are only half cones. And in the, let me see if I can make this thing work forwards to the next picture. No, I've done the wrong thing. Why have I done the wrong thing? Oh, I pressed the key on the board, on the machine, don't I?
Sorry, press this one. Here.
Oh, it's that one. Yes, I have the right computer. Thank you. This is a null cone, or I may call it a light cone. it's really a null cone. At every point in space-time, you have one of these cones. And in the picture that we just had, let's just see if I can figure out how to go backwards on this thing. Yes. In the picture we just had, I have only the half cones mentioned, drawn. So you have to imagine those little cones, there is a back cone to them as well. Sometimes I draw both parts, sometimes not. In the picture, I just had the future part. But this is a null cone. What does that mean? Well, you see, we're talking about 4 dimensions. So we have the 3 spatial dimensions. At any point, you say, let's have 3 spatial axes, x, y, and z, and a time axis, t. And I want to choose units so that the light ray represents something. It isn't just flat on the ground or something like this. So that if your time units are perhaps seconds, then your space units would be light seconds, how long it takes, how far light can go in a second. So you have to have comparable units, and that means that your light ray will look like something comparable in the picture. So the yellow thing represents the path of a photon, if you like, just going at the speed of light, tilted at, roughly speaking, 45 degrees in the picture. Now, let's see, to make the thing move forward. No, I'm moving it backwards. There we go. That's the light ray. And this cone then represents not just that one light ray, but all the light rays. And we don't need the axes, we just need the cone. So it represents possible light rays emitted from that origin point. Okay, your space-time will have these things all over the place. There's not necessarily any uniformity about the arrangement of these things, so I have them looking fairly random in this picture here. Whatever the metric of the space-time says, this cones will be in accordance with that. Now, I want to talk back again about this picture, which appears in my paper. You see the shaded region, you see the trapped surface there, and I hope I can master this thing here. This trapped surface is that little represented by the ring, and the shaded region indicates the future of that ring. So you're looking at all the points which can be reached by particles traveling, say, less than or equal to the speed of light, and they sweep out that shaded region. What I'm concerned with is the boundary of that region. So you're looking at where that region stops, the boundary of it. And you can prove various theorems about boundaries of futures, which I had convinced myself about. Let's see, I haven't mastered this thing yet, do I? Moving forwards, oh no, I do that down here, don't I? Here we go. Yes. Now you see, the light rays will start crossing each other in various ways. The boundary of the future is generated by these rays, so you see these lines. We imagine this is part of the boundary. The future is on the top side, and the outside behind the future is this other side of the surface. But the surface will start crossing itself and do horrible things like this. So you see these caustics and crossing regions, and that's the generic thing. In a general solution, they'll start crossing each other and do horrible things. But the nice thing is that if you're looking at the boundary of a future, you don't need to look at all these horrible caustics and so on. All you look at is just stop off where the lines start to cross each other. So it actually makes quite a topologically decent space. It may not be very smooth, certainly get wrinkles in it, like where they cross over, but it's a nice topological space. It doesn't cross over and has a nice structure like that. And so I was able to use that property, and the fact that this was a sort of theorem I could show was true, that if you take any point on the boundary of the future, then I seem to have lost here we go, any point on that, you will see that there will be a light ray going back into the past. It may stop and cross over with something else into the future, but it always keeps on going back and back into the past, and that was the key thing. It goes back into the past until it reaches that's crossing the, yeah. I'm sorry, it's jumping. I don't mean to do this. Why is it doing that? Okay, we just have this picture. Now I want to say something about light rays. This is something I learned at school. I didn't learn all that many things that were useful for this at school, but one of the things was we used to play with these optical benches, and you could have lenses on and look at how the lenses behaved and sequences of lenses and what they did. And if you have a positive lens that focuses the rays inwards, and magnifies what you're looking at. A negative lens will bend the lines outwards. I don't remember having astigmatic lenses, we may have had, but this is the key point I want to mention here, that the light rays, in fact, I think I'll move over to the next slide if I can do that. I'm imagining now we're sitting at some point in space-time right at the top, and you're looking back, so the light rays into our point will encounter curvature of space-time. Now, the curvature of space-time will be of two kinds. One is what's called Ricci curvature, and that's what Einstein's equations tell you behave like a positive lens. As long as the mass is positive, not negative, then it will act like a positive lens. So in the optical bench, you've got these positive lenses which magnify. So that's what the matter, as the rays go through matter, they start to focus inwards. When rays enter the other part of the curvature, see what I learned about the spinners when I started playing them after Finkelstein's talk, that you could split the curvature of space-time into two pieces, and they look very beautiful. One of the pieces is what's called the Ricci part. That's what Einstein tells you the matter does. It gives you a contribution to that. And what Einstein didn't talk so much about is the other part, which is the Weyl part. And the Weyl part we'll come to later. It's a very important part of the curvature. But roughly speaking, it is the gravitational field itself. It's not the source. The Ricci part is the source of the field, and the Weyl part is the field itself. And what does the gravitational field itself do? Well, it does purely astigmatic focusing. So it's like a lens which is convex one way and concave the other way, and the convex part magnifies and the concave part minifies, and the amount of magnification exactly balances the amount of minification, if that's a word. So, but when the optical bench, you slide these things away, and what you notice is there's a nonlinear effect. If the lenses are all close to each other, they simply add up. But when you move them apart, then there is an additional inward focusing part. And so it behaves like mass being there, but it's a sort of non-local. It's actually the energy in the gravitational wave that you're seeing. So that whatever you have, if you have matter for which the mass is non-negative, then you have inward focusing, positive focusing. If you have vacuum, that is the part, where are we going? Yes. The Weyl part, that's just the gravitational field itself, then if that's complicated and it does lots of oscillating backwards and forwards, it behaves like the Ricci part. So whichever you have, it causes positive focusing. And that's the key point. I think I want to go back to the previous one, if I can remember how to do that, which I'm not very good at. Here we have, now, this is think of the expedition that Eddington made to check up on Einstein's theory to the island of Principe, and he was looking at during an eclipse to see what the effect on the star field behind the sun was. So when the sun is blotted out, I'm going to imagine that even though the sun is blotted out by the moon, forget about that, you're looking at the rays of light which go through the sun, and you should imagine that the sun is transparent and that the rays are only bending due to the gravitational focusing effect. So you're looking at the Ricci part, so the sun is acting like a positive lens. You're not actually seeing that part, you're seeing the part just outside that. But since the sun has magnified the field behind it, then that means that the empty space behind it will also be pushed outwards. So the stars that you're looking at, the images will be pushed out by the presence of the sun, and that was the effect that Eddington was looking for. But you see in this picture, I have the pushing out, I keep pressing wrong buttons. The pushing out gets less and less as you go further out, because the effect fades away as you go out, so that the radial amount is less and less, whereas the transverse part, as you're going further out, will be magnified, so that a circular shape will be distorted into an elliptical shape. That's the point I want to make. And this is just the magnifying effect due to the sun being there, and now the sun's field is what you're looking at here, which is the Weyl part. You're looking at the Weyl part, and that is causing the distortion that you're seeing here. So it's an illustration of the other picture which I just showed you, where you see that the empty space gravitational field causes the Weyl distortion of the image, whereas the Ricci part, which is the matter itself, the positive energy, causes a magnification. And you can see them illustrated in this picture here. Okay, let me move onwards. And I just talked about that. Yes. Just to finish the story, perhaps about here, the story was that when you look at the future of the trapped surface, it starts by converging. You see what I said, the trapped surface, you're looking at the future of that, the flash of light which goes out or the flash of light that goes in, both of them are inwards, and since the focusing is always inwards, that means that they will come to crossings over and things like that, and this boundary of that future will come to an end. And it will be what's called a compact region. And that compact region, then you see how it could have come about from an initial surface. And that gives you a contradiction to, well, in the paper I didn't say what really happened. And I think I listed various possibilities. One of being perhaps quantum gravity takes over, which I'll say a little bit more about shortly. But the general thing is that you can't get away from some problem. The problem is what you call a singularity. Presumably means that densities, curvatures become infinite, and you just can't continue after that. So that was really what I showed. Actually, it's curious that we had the citation for the Nobel Prize, which was just given. But what I allegedly showed was that black holes were a robust prediction of the general theory of relativity. Strictly speaking, what I showed was that singularities are a robust prediction of general relativity. And that is true. It doesn't tell you that you get black holes. In fact, I was a little unsure about that myself. You could possibly have something worse than a black hole, which I used to call a naked singularity. You could have singularities which are there, but you could see. And it's, as far as I'm aware, it's still not proved that in a general situation you don't get naked singularities. It's a missing part of the story. But the black holes are much, you might think they're wild enough, but naked singularity is a lot worse. But I did contemplate the possibility that they might be there. But I think the answer is that you get black holes and not naked singularities. I thought of that as slightly disappointing, actually, but never mind. That's what we have. Black holes, that's fine. They're interesting enough. Good. Okay, let's move on. Now, you see, I gave this talk, when I say this talk, I haven't mentioned it yet. I gave a talk at King's College, again, King's College, I think it was King's College, on the singularity theorem. And I think it probably was Felix Birani who asked me to give that talk. I can't remember how he found out about it. I remember being very pleased that the geometer relativist J.L. Singh, who I'd read his books and I was a great admirer of his work in general relativity, he had this geometrical way of thinking which I fitted in with very much. And he was present at the talk. According to the movie, Stephen Hawking was at the talk, I think with sparks coming out of his head or something, being inspired by the talk. He wasn't actually there. Never mind. I was proud. I didn't know anything about Stephen Hawking anyway at that time. But J.R. Singh was there, and I was very pleased that he was there. But Dennis Sharma heard about my talk, and he asked me to give a repeat at Cambridge, which I did. And yes, Stephen was there. Not only was he there, but we had conversations afterwards with George Ellis, and I went into the details of the type of argument I was using. Stephen very quickly picked up on these arguments and started to apply them to the Big Bang singularity. You see, you have the singularity in the future where curvatures seem to become infinite and everything goes crazy, densities go infinite. And then what about the past? Well, you have the Big Bang. And the Big Bang seems to be something very similar, and maybe the same types of arguments can be used for the Big Bang. Well, it was a bit hard to use them directly because the argument I used depended on compactness and a non-compactness inconsistency, and that doesn't necessarily work for the Big Bang. But Stephen very quickly picked up on the arguments and started to produce a string of theorems generalizing the techniques I was using and using very clever ideas which enable you to talk about cosmology as a whole the same way. So that was, one thinks of these things as two sides of the same coin. The collapse gives you, in general situations, singularities, and the Big Bang, if you imagine, instead of having a Big Bang, which was the beginning of the universe, but maybe there was some complicated stuff which went swishing around and came swirling out again, that might have been what the Big Bang was like. But then Stephen's arguments were showing that that is not what happens. That is to say, you will still get singularities in generic situations. And he got more and more general theorems, and then we collaborated on the final theorem. He had 3 in the Royal Society proceedings, and then we had a 4th together where we had a more general argument which pretty well included all the others. Okay, that's just the story of the singularity papers. And so, okay, that tells you get singularities. However, there was something very strange about this which worried me. This is the following. I have to move forward. I need to do it here, don't I? Suppose we had a collapsing universe. You see, everything is just the same. All the arguments work one way in time, they work the other way in time. They're completely symmetrical in time. So they don't tell you anything asymmetrical in time. So they would apply to a collapsing universe. I should perhaps point out one thing about this picture, which maybe, and about the one we just had. Perhaps I'll go back to that. I wanted to indicate a universe. In the remote future, we have, or not so remote now, in the future we have this exponential expansion. That was not known at the time of all these theorems. This is what people refer to as dark energy. I prefer to call it Einstein's cosmological constant. Einstein introduced this term for the wrong reason. He was trying to have a static universe, one which was not expanding or collapsing, but then he was rapidly convinced by Hubble and people that the universe was actually expanding, and so this reason for introducing this cosmological constant, which enabled him to have this static model, he then retracted it and said it was his greatest blunder. It's curious to know that even Einstein's greatest blunder turned out to be true, as we seem to have the feature predicted by this cosmological term, this exponential expansion. So that is explaining this. As I said, we didn't know about that at the time, but observations round about at the turn of the century seem to indicate that this is what the universe is actually doing. I should explain, on the other hand, the back, we have all that frilly stuff. What's that doing? It's just that I don't want to prejudice the issue as to whether the universe is closed up, spatially closed, or open. It might be either. And the arguments that I want to come to later will apply either way. So I'm not really worried about whether it closes. Well, it's an interesting question, but for the purposes of the things I'm going to talk about, it doesn't matter whether it's closed or open. So I've given that thing a bit of continuation at the back if it wants it. So we'll leave it at that. Okay, so that is the sort of picture we have of the universe as we understand it now. Forwards is this way, isn't it? Now, what about a collapsing universe? Collapsing universe, okay, that's a model, but it's nothing like what you would expect. Why not? Because you will, if you have a general, you see the models like with the collapsing dust cloud and all that, when you have an exactly symmetrical thing, you get something a bit special, and it may be critically special. What happens in the general case? So what happens in the general case here, you would expect to have irregular clumping of material, and they will produce black holes at various times, and as the universe gets more and more dense, you'll get more and more black holes, and the black holes will start to dominate and eat each other up and produce one horrible mess. Look like that. It will look much more like that. So this is my picture of a collapsing universe producing some horrendous mess at the end. Now you see, why wasn't the Big Bang like that? A horrendous mess, and with, well, white holes, or whatever you might call them, coming about and being nothing like the universe we see. So I began to worry about that a lot. I've a little bit forgotten what the order of my slides is, but let's talk about this first. See, why isn't the universe a great mess? Well, one of the arguments I think people tend to say, well, inflation takes over. What's inflation? Well, I've got a magnifying glass to have a look at it. It's something which is supposed to be happening right at the very beginning. I don't think I've quite mastered this thing yet. Okay, the magnifying glass is supposed to be looking at this, and what, according to the inflationary scheme of things, there will be... Oh, what's it happened? Something has got in the way. Can you get rid of it?
There you go.
Thank you. What you see is, according to the inflationary scheme, something very similar to the exponential expansion in the remote stages. So that's the idea, and that if you have lots of irregularities, then maybe they will all get ironed out by this inflationary phase. I wasn't at all happy about this, and I may say I'm not at all happy about inflation anyway. I'll have to say something about that later, because it is a part of current cosmology, a very significant part of current cosmology, but I'll say a little bit about it later. My disbelief of it, which will come, how I get away with that, if you like. Anyway, this is what you expect to see, but it doesn't solve the problem, because whatever physics you put in here, you put in a thing called the inflaton field. You put the inflaton field in. If you have this great mess, which I was talking about before, this one, putting the inflaton field doesn't even get a start. It doesn't do anything. So that doesn't explain why we don't have this at the beginning. It'll only iron out some things which are pretty smooth already. It doesn't solve that problem. And it certainly can't, for a very good reason. Let me move onwards. No, that's right. I want to talk about the second law of thermodynamics, which is crucial to this part of the story. You see, what does the second law of thermodynamics tell us? It tells us this thing called entropy is increasing with time. Entropy, roughly speaking, is a measure of the randomness of the situation. So it's telling you the randomness increases with time. Okay, so you've got that picture. That's a very important law of physics, very crucial to all sorts of aspects of physics. Entropy is increasing with time. Okay, that means that if you go to the very remote future, the entropy will be very high. As you come back and back and back and back, the entropy will come down and down and down. What's the earliest thing you see? Well, it's the microwave background. That is where the photons, previously they've been scattering around, and finally they escape. And what you see as these microwave background photons coming out. And what you see, this was the first satellite, the Kobe satellite, I think, and the wonderful thing that they saw was this wonderful curve. I should explain this curve. It's what's called the Planck curve, and the thick line in that thing, in the curve, continuous thick line, is what's called the Planck curve. I'll come to that in a minute. And the error bars are these lines going up and down. However, the error bars are magnified by a factor of 500, so that means that the real error bars are only 500th as long as the error bars. So even the worst ones, right at the end down here, are within the thickness of the incline, well within the thickness of the incline. So it's a very perfect Planck curve. In fact, I'm told it's the most perfect Planck curve ever seen anywhere. What does the Planck curve tell us? It tells us you're looking at thermal equilibrium. It's what started off quantum physics, and it has to do with, I'll come to that, a little bit about that later. But this was, at the turn of the century, Max Planck had an explanation of this curve which depended on energy being in little bundles, which I'll say something about later. But the main point I'm trying to make is what you're looking at, the Planck curve represents maximum entropy. Maximum entropy. So you're going back from the future, you're coming down and down and down and down and down until you reach your maximum. Maximum. I never could understand why people weren't more puzzled by that. I mean, I don't know why they weren't more puzzled by that. Because, sure, you're seeing a maximum. Now, you might think, well, okay, the universe is expanding, so maybe there's something complex. That's not the answer. You can see quite easily it's not the answer. I won't go into that now. No, there is something very puzzling about this. What you're looking at is a maximum entropy, whereas why isn't it a minimum of some sort? Well, that's because of the next picture, which I keep getting confused by these buttons. Here we have, this is my one picture where time is going from left to right rather than upwards. The top three pictures represent something like a gas in a box. It doesn't have to be any old gas. It's quite a generic thing. You imagine your gas is tucked up in one corner of the box. You open the box up, the small box, that is, and it finds its way into the big box. Entropy increases from left to right. Uniformity increases from left to right. So if you have most things in nature, certainly an ordinary gas, then the increase in entropy is accompanied by an increase in uniformity. The bottom three pictures represent a galactic scale box now with a lot of stars running around. Now those stars, I'm starting them off, and now entropy is still increasing from left to right, but the picture looks quite different. It looks the opposite, in fact. What you're having is an increase of non-uniformity, a decrease in uniformity from left to right as time increases. And in fact, the black hole represents a huge increase in entropy. There's this formula due to Bekenstein and Hawking which tells you what the entropy in a black hole is, and the entropy goes absolutely shooting up. So that's what's happening according to the second law of thermodynamics. You expect left to right in all these pictures. What do we see? We see Planck's spectrum, consistent with the matter being the radiation and material being in thermal equilibrium, in other words, maximum entropy. And you see the top right-hand picture. As far as the gravitational effects are concerned, we're seeing bottom left-hand picture, completely the other way around. So what we're seeing is what is the lowness in the entropy in the universe here in this early stage? It's in the gravity, only in gravity. And for some reason, I didn't know why people weren't more puzzled about that. Now let's see, the forward going is down here. Okay, it's done it already for me. This is a nice picture which is described by Schrödinger in his book, What is Life? I read that book and got a lot from it. You might say, what do we get from the sun that keeps life going on Earth? Well, people often say, oh, we get energy from the sun. That's completely wrong, as Schrödinger pointed out very clearly. You see, the sun is a hot spot in a dark sky. In the daytime, yeah, we get energy from the sun. In the night, it pretty well all goes back into the sky. In fact, there's a little bit less because of global warming, but this is a much, much huger effect, which I'm talking about here, which is that the key point is that the sun is a hot spot in a dark sky. The temperature of the sun is much greater than that of the sky. What does that mean? Well, according to the Max Planck formula, it means that the energy from the sun comes in much more energetic photons. So the photons are individually much more energetic, much higher frequency, and the ones that go out are much colder, infrared, and therefore they carry individually less energy. Therefore, the energy is spread over many, many more degrees of freedom when it goes away, and many fewer degrees of freedom as it comes in. And what we live off is not the sun having a bright spot in the dark. If the whole sky was as bright as the sun, it would be utterly useless. There wouldn't be any use whatsoever. What is useful is the contrast between the bright sun and the dark sky. That's Schrödinger's point. He made that point very clearly. Lots of people didn't understand what he was saying. And that, you might say, well, the important point, you might say, well, what's happening with the sun? Why is it a hot spot in the dark sky? And people say, well, nuclear forces and all that. Well, that's true. But the main point is the sun is there at all. If there weren't any nuclear forces, it would still get hot, even much more quickly. It's just that the nuclear reactions slow it down and make it nice and comfortable for us. But that's not the point. The point is the sun is there at all, and it's there because of the clumping of the material into hot bodies, the uniform distribution becoming hot in these localized places. And that we're taking advantage of the low entropy and the uniformity of the material in the early universe, and that's what starts off the second law of thermodynamics. That's why we're all here. That's the basic reason for it. And that's because the universe started off with very little activation of the degrees of freedom in the gravitational field. Okay. Well, I used to say, well, like everybody else, and still like everybody else in a way, how do you deal with the singularities? You want a new physics. What new physics is it? Well, the curvature gets very, very big. That means the radius of curvature gets very, very tiny. It gets so tiny, really, really, really tiny, that you have to start worrying about quantum gravity. What happens when you combine these two great theories of 20th century physics, quantum mechanics, quantum field theory, and Einstein's general theory of relativity? When we combine them, so people say, well, we will understand the singularities and that will resolve all these problems. It doesn't. Well, it doesn't unless quantum gravity is a very peculiar theory, which I suspect it is. But I spent a lot of time thinking, oh, well, it's got to be a very time asymmetric theory. And it deals with the singularities by producing these very special ones in the Big Bang, the singularities which have to be very uniform, Weyl curvature free. This is the gravitational degrees of freedom are described by the Weyl curvature, and these Weyl curvature degrees of freedom seem not to be activated in the beginning. So it's really just this is stating what I call the Weyl curvature hypothesis. It says, okay, for some reason unknown, maybe some very peculiar quantum gravity theory, the singularities go to infinity. They're only allowed to do that in future direction. In the past direction, they have to go to zero. That would explain what we see, but it's not a very good why if we're looking for something combining GR and quantum theory. I want to digress slightly. I think that's what I'm doing in the next slide. I have to remember what the next slide says. Digress slightly to say that I do think that quantum gravity has to be a very peculiar theory. And you see, what's very special about gravity is that it has what's called a principle of equivalence. I think there's a great irony in the history of physics that gravity was the sort of archetype of physics as a whole. And Newton, when he wrote his Principia, studied all sorts of force laws other than inverse square. Of course, inverse square was the great thing and showed that the Kepler orbits and all that stuff worked. But it was the sort of a start-off of all sorts of other kinds of forces you might have. However, what is special about gravity is this principle of equivalence. And at the top we see some Galileo, or his imaginary Galileo, dropping a big rock and a little rock. And he knew perfectly well that if they don't fall together, it's because of air resistance, and you have to get rid of that. He was perfectly aware of that. And he considered that the big rock and the little rock would fall together. I remember reading in his works that he described fireworks. You have these fireworks, and there's a great explosion, and you see the spherical pattern of the sparks. And as they fall, that remains a sphere. And he points this out. Shows that when you fall freely with gravity, you cancel gravity out. It's the only force in nature for which that is true. And that makes it special. Here, at the bottom picture, you see a sort of 2001 type space station and an astronaut. Even though the Earth is there, the astronaut seems to be able to cancel gravity out pretty well just by falling freely. And falling freely can be in orbit. You don't have to fall downwards. Now, you see, I won't go into this calculation here, but this is a calculation to show there's something funny about trying to combine the principle of equivalence with the principle of superposition. See, quantum mechanics allows you to say if one thing can happen. In the first lecture that I heard Dirac give, I think he had a piece of chalk, and he talked about atoms can be in two places at once, according to quantum mechanics. What about the piece of chalk? Can that be in two places at once? And he tried to, I think my mind wandered when I heard this lecture, and I didn't hear the explanation, which is just as well, because I've worried about it ever since. Why can't pieces of chalk be in a superposition in two places at once? Well, here you see there is an argument, which I went into. I won't go into the details of it. But there are two ways. I'm imagining you're doing an experiment on a tabletop, and you want to do quantum mechanics, and you want to write down the wave function and things like that. And how do you do it in quantum mechanics when you want to take the Earth's gravitational field into consideration? Well, any sensible physicist would do what they do for every force. They would put a term in the Hamiltonian and just chug away, and that's what you do. Don't care if you don't know what that means, don't worry. The point is that that's what I'm calling the Newtonian way of doing it. Now, what would Einstein say you should do? No, you don't do that. The gravitational field, you do the Galileo thing. You imagine free fall, there is no gravitational field. Do it all over again with a coordinate system which is falling freely, and do you get the same answer? almost get the same answer. You get the same answer except for what's called a phase factor. And you have to know about quantum mechanics and all that to know why that's not important or is important. It's not important because you don't care about phase factors. If you're only going to work out probabilities, they disappear. However, it is important if you're worrying about what the vacuum field you're talking about is, and it does make a difference. There's a funny term up there with a t cubed in it. Don't worry about the details. All I'm saying is that there is a problem with the Einsteinian perspective in this picture. And when you consider, it doesn't matter too much when you've just got the Earth field, but when you want to consider a field of some body which is part of the system, which is being put into a superposition at two places at once, so that's the thing at the bottom, where I've got the brown thing and the blue thing. That's meant to be the same body in a superposition of two locations. And you try to use the Einsteinian point of view, and you land in trouble. I won't go into the details, but you land in trouble, and a way of resolving that trouble is to say that that superposition between those two locations is unstable and will become one or the other in a time scale that can be calculated. And the calculation is, oh dear, it's jumping away. It's not what I want to do here at all. I'm going backwards. I'm pressing the wrong key, I think. Yes. Oh dear. Let me forget about all that. Anyway, there is an argument which seems to suggest that superpositions of macroscopic bodies will have a lifetime and will only last a certain length of time. And it's quite consistent with Heisenberg's uncertainty principle and things like that. Anyway, I only mentioned that just to entertain the experts or something. What I want to say is I couldn't really make anything of that, except that I think that when you think about quantum gravity, it's going to be a strange theory. It's not going to be an ordinary quantum mechanics. It's going to be a theory which differs from standard quantum mechanics. And I do believe that's the case, and I believe that it will, when we find it, will resolve the conundrum of the collapse of the wave function, which is why you don't find pieces of chalk in two places at once and all that sort of thing. Now, I want to take a different route now. This was not something I thought of initially, but it's a different route, which I owe partly to who was a student of mine at the time, a graduate student, Paul Todd. And he said, why not use your idea of saying the vowel curvature is zero, but use a slightly different idea. What I'm describing here is two ideas. One is what you do to infinity. The left-hand picture represents the universe expand. It's a smaller version of the picture you saw before. And when you have a positive cosmological constant, you can squash down infinity to make it into a nice boundary, which I'll say a little bit more in a minute. You can also stretch out the Big Bang, and Paul Todd's idea was what is special about the Big Bang is you can stretch it out to make it a nice smooth boundary, which you could imagine extending. You don't think it really extends, but it's a nice smooth boundary. So the idea is you get smooth boundaries both in the past and in the future. So this was his way of saying the vowel curvature hypothesis. It was much nicer than my way because you could start to do calculations in a serious way, which is what he did. I'm not going to say too much about that now, but let me go on by pressing the right button, I hope. Here we have a nice picture due to M.C. Escher explaining what happens when you squash infinity down in a conformal way. Conformal means, well, you squash it in all directions by the same amount. This is a very beautiful one of Escher's circle limits. It's the first one. It's the one he was least proud of because it's closest, I guess, to the mathematical model. But nevertheless, it's a very beautiful picture. I like it a lot. And you can see the eyes of these fish creatures are circles. And this illustrates the conformal nature of this mapping. It represents a kind of geometry called hyperbolic geometry. Don't worry about that. But in this kind of geometry, you can represent it as the interior of a circle conformally, so that the fish themselves, think of them as the same no matter how close to the boundary are. That boundary represents infinity for the fish creatures, and it's conformal because it squashes their eyes both ways at once, so they remain circles right up to the edge. I've seen the original of this picture, and it really is remarkably accurate right down to the edge there. So it represents what you can do to infinity to make it into a nice smooth boundary by simply this conformal squashing. And Paul Todd was suggesting making a conformal stretch to the other this way, isn't it? Now, what does conformal mean for space-times? Well, you see, when I talked about null cones, I was talking about most of the metric. At any one point, the metric, which just defines distances and things and times, the metric is a quantity which depends on 10 numbers. Now, 9 of them are giving you the conformal structure, or in other words, the light cone or the null cone. Those 9 are really the 10 independent ratios. Sorry, the 9 independent ratios of those 10 components of the metric. So you're not taking the whole metric, you're taking the conformal metric. So that's the scale, the part which is not changed when you scale. So you scale in and out, like with those fish. And you scale the time in and out by the same amount as you scale the distance in and out. So that's conformal. Now, here I have a picture with the whole metric represented. So you have something else. You have these bowl-shaped surfaces in the top cone and the hill-shaped ones in the bottom cone. Those represent the tickings of a clock. Here I'm imagining 2 particles whizzing by. They're not photons now. And they intersect these surfaces, tick, 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 tick. And as the different ones with their different velocities, their ticks are represented by where they intersect these surfaces. So that's fine. And the nature of this comes about from the 2 most famous formulae of 20th century physics. E equals mc squared. C is a constant. E is therefore the same as m. E and m are equivalent. Energy and mass are equivalent. That's Einstein. Max Planck, preceding Einstein, in the Planck spectrum and all the thing which I mentioned before, he says E equals h nu, or F. Nu is a frequency. So energy and frequency are equivalent. H, again, is a constant. Put the 2 together, that tells you mass and frequency are equivalent. So a mass is a clock. And it's fundamentally a clock by these 2 famous formulae. Okay, that's the fundamentals of nuclear and atomic clocks and things like that. But you have to scale it down to make things you can actually handle. But the basis is the same. So when you have mass, you have clocks. You need these bowl and hill-shaped surfaces, not just the light cone. You need them too for the metric. However, going the other way, suppose you don't have any massive particles. Suppose you just have massless things. Well, the massless photon zips along the light cone or the null cone. It doesn't encounter these surfaces at all. So as far as light is concerned, you're just interested in the null cones. You don't care about the scaling of them. So, okay, now, forward moving is this way, isn't it? So you're interested in just the cones. Okay, now we go back to here. Just say we're interested in only the cones. Now, does this picture make physical sense as opposed to just geometrical sense? Well, in a certain sense, it does. What about the remote future? Well, the remote future will be dominated by photons. Photons don't have any mass, so they don't have the scale. They're basically just interested in the light cones. There's a bit of a problem because you do have some massive things. I can go into that if people want to know. But the argument I have is that massless things dominate the remote future. And photons, like in the Escher picture, they just go zipping right through and they don't bother about the edge at all. They come out the other side and say, why am I over here? There's no universe left. Well, you see, the idea is, I'll come to in a minute, do they come to something, those light rays? What about the Big Bang? Well, they've stretched it out. And what about the physics? Well, you see, along with the stretching of lengths and, in the remote future, I'm squashing down lengths and times. There's a comparable, there's a physical concept. Lengths go to momenta and times go to energies. So they're the opposite features. And they do the opposite thing. So this means that your energies, you have a very, very cold and rarefied remote future. When you squash it, it gets hotter and denser. The Big Bang is very hot and dense. When you stretch it, it becomes colder and less dense. So they seem to be rather similar. In fact, that was the idea. They look rather like each other in a certain sense. Are they more like than even just that? Maybe. Am I going forwards? Yes. You see, the picture we just had is, I want to say, not outrageous. It's a particular thing which doesn't go against people's views. I don't know about inflation, but it doesn't normally go against people's views. You could imagine doing a thing like this. However, what I'm saying is that there was something before the Big Bang. There will be something after the infinity, remote future. And it will be another, what I call an eon. Our eon, you have to imagine, is the one in the middle. It doesn't make much difference because they're all similar to each other, rather. That's our eon here. And I've stretched out our Big Bang, and I squashed down our remote future. And I'm saying that our remote future will become the Big Bang of the next eon. Our Big Bang was the continuation of the remote future of a previous eon. I used to go lecturing on this thing lots of times to people, and I could think, well, nobody will ever prove me wrong, so I can go on forever talking about it. And then I thought, maybe they can prove me wrong. And the idea I had, well, first of all, things can get across. Massless things can get across. Photons, as long as they were long enough wavelength, maybe the magnetic fields that I think I mentioned, or gravitational signals certainly, could get across. So that is possible for things to get across, as long as they're massless, photons. But what about, now you see in this picture, I'm imagining that we are up at the top. That's us looking back. That's our past cone. This is the crossover surface between our eon and the previous one. Imagining in the previous eon, we have a cluster of galaxies. In that cluster, there are supermassive black holes that now and again run into each other. Like us, our supermassive black hole, our big black hole in the center of our galaxy will get swallowed up by the Andromeda one in a few thousand million years when we collide with it and spiral around and it swallows us up, I guess. It's a lot bigger than ours. That we're not going to be around to witness that, but somebody might in the next eon see it. You see here, I'm imagining in some cluster of galaxies, some supermassive black holes start running into each other, and they produce gravitational wave signals, and those gravitational wave signals might be seen by us. The best way to imagine this is you have to add another dimension, so that crossover surface is three-dimensional. The things which look like circles are actually spherical regions. When they intersect, you will see a ring of intersection. So we would look back, and if we can see in some way the effects of these gravitational wave signals, you might see a ring in the sky. I was considering the effect on the microwave background, and it should produce either a heating or a cooling, depending on whether they're far away or close to us. It's the opposite way than the way we'd think. But nevertheless, it would affect the temperature. I tried to get some people to look at this. Some people in Princeton did. They did it in a way which I realized afterwards there's no hope they would see anything. They didn't see anything. Vahe Gurzajan, who is an Armenian colleague of mine, did it a different way, in a way which I thought was, for my purposes, more promising, because the way he was choosing these things, you could see whether your rings were concentric or not. You see, if you have, in a cluster of galaxies, you have more than one occasion. You see, one cluster, there'd be several of these explosions, bang, bang, bang. It's not really a bang, of course, but the gravitational wave signals will go up, they will disturb the microwave background, and we would see an effect. What Vahe looked for was an effect where the temperature around the ring was anomalously low. That's to say, not the temperature was low, the variation in the temperature around the ring was anomalously low. So, and the signal was pretty weak, so you'd have to look for three concentric ones to have an effect that he would notice. So that was what he looked for. And let me just see, to move on, but I keep getting confused by this. This is the result of, he did lots of pictures like this. This is the result of looking at the Planck's data, the Planck satellite data. And what are these? These are looking at centers of low variance rings where you see at least three of them. And the centers are the spots you see. Now what's remarkable about this picture is the clumping. You see them not uniform over the whole sky. So even if it's not what we think we're looking at, what is it? there is this thing called the cosmological principle, which says that the bigger you look, the more uniformity you see. Doesn't seem to be true if you look for these signals, whatever they are. If they are what I think they are, there's something else you can tell from this picture. You see, he picked these out. The coloring of the points here is determined by the variance of the temperature, not by the temperature. If now you look at the temperature around the ring, the red ones, as it turns out, are due to two peculiar things together. They are actually, according to the theory, the more distant ones. The blue ones are the relatively close ones. So the blue ones are within our particle horizon, it's called. The red ones you shouldn't be able to see at all, except with signals like this, because you can see outside a particle horizon in the previous eon. Never mind about the details there. But the point that's remarkable is that the clumping is not just where you are, in other words, the sort of angular relationship to us, but in the distance from us. So these are clumped regions, clumped in color, which seems to suggest, according to the theory, that means it is simply a clumped region, where the blue ones are less distant and the red ones are much more distant. There could be effects that these things, other effects, and we think maybe there is some evidence of that, but it's all less robust than this. You see, this picture is just there, and he's got several pictures looking just like this. So if it's not what I'm saying it is, I need an explanation for the clumping, and both in color and where they are. Okay. Now I'll come to the other signal we're looking at. These are, I should say, a Polish group also look quite differently, and they also see effects of this kind that I've just shown you. So that it's not just Vahe's analysis, it's the analysis also from the Polish group, looking a very, very different way of doing it. And they also seem to see signals with, I think, a 99.4 confidence level. Not huge, but pretty confident something is there. Now, this is another effect. This is something which I'd thought of before, but I never really thought of looking for it. You see, this is what happens to what happens to a cluster of galaxies. A cluster of galaxies forms a black hole, eventually, a supermassive black hole, swallows most of it. Some of it will escape. Probably most of it gets swallowed. And this black hole sits around, and after something like 10 to the 100 years, a long time, it will evaporate away by Hawking evaporation. That evaporation carries away the entire mass of the black hole. How much of the information it carries away is an interesting question. It doesn't make much difference in what I want to say, but it's an interesting question. You should expect to see you see, you imagine the Escher picture, which we had earlier. I think, I don't know if it's worth going back to it. If you get close to the edge, you see, everything is so crowded there. So in the picture, the cosmological picture, everything gets very crowded towards the edge. And this means that the Hawking radiation here actually is very, very concentrated into a very, very tiny region, virtually a point. So the entire mass of the black hole, or most of the cluster of galaxies it came from, will be concentrated in the crossover surface into one teensy-weensy little point. There's another thing which I think I've left too little time, it's probably a negative time, so I can't talk about it. But people talk about what's sometimes called the information paradox of black holes, and that somehow, well, some people say the information is swallowed up, and Stephen Hawking said both things at different stages of his life, that maybe information gets destroyed or it doesn't. And it doesn't make much difference to my scheme. This is, the Penrose diagrams were mentioned, and this is one, so you can see one on the right-hand side there. But it does indicate that the singularity, which is the wiggly line, is space-like. And that means that how on earth do you get information? It swallows information. So I really can't see how you get information back, no matter how hard you struggle. And I think it does swallow information. It doesn't make any difference to the scheme I'm proposing, because what happens to the information? Well, you've got to have something happening to the information, because the entropy has to come down. In the next eon, what happens? Well, the information, all the entropy, all the degrees of freedom, pretty well, go into the black holes. They go into these Hawking points, as I'm calling them. Let's go to the next picture. I think I have to do it this way, don't I? This is a picture from the paper which was written by Christoph Meisner, Pavel Nurowski, Daniel Ann, and myself, published, I guess, nearly 2 years ago. I can't remember now how long it was. A fair time ago, in the monthly notices of the Royal Astronomical Society, and we seem to see these, what I'm calling Hawking points or Hawking spots. The horizontal line at the bottom represents the crossover surface. So down here is the previous eon, according to this picture. Above it, well, there's something else right at the top, so don't worry about that too much. Up to about here, above it is our eon. This is us looking back. We're looking back. What do we see? We see the last scattering surface. That's that surface which I had drawn before. The last scattering surface. And here we have the galactic cluster, or the entire Hawking evaporation will be tucked up right in this little tiny point here. So it's really essentially all happening at that point. Whether the information gets destroyed on the singularity, whether it goes into the Hawking radiation, whether it's half and half, I think as Don Page suggested roughly, it doesn't make any difference for this picture. You get a huge amount of energy coming through, and in fact, you might say, what happens to it all? It doesn't get lost, because you can do integrals. You can show by looking at the conformal structure, which is smooth right across the surface, that it doesn't get lost. Something must come through to the other side. It bursts its way through 380,000 years. That is the gap between this first horizontal line and the next one. That is the microwave background radiation starting. Before that, it just scatters around and doesn't escape. Right now, the stuff gets cooled out enough that the photons can finally escape. And you see a spot, which is the Hawking point here, spread out to about 4 degrees across the sky, or 8 times the radius of the full moon. That's what we see. So we seem to see these spots with a confidence level of 99.98%. So that is the level of confidence, much stronger confidence level than we saw before. The analysis that Christoph does doesn't tell us where the spots are. It just says that there are spots with that confidence level of that size. That's what it says. Now, what just one final point I want to make is if you look at what seem to be the 6 strongest points, you can locate where they are in the sky. You now look in the other satellite data. This was in the Planck satellite data. You can look in the W map, the older one, which is a different way of doing the analysis, all very different. And you look for those spots. And you see them they are also in the W map data in exactly the same places. I said 6, those were 5 spots. 5 strongest spots in the Planck data are seen in exactly the same places in the WMAP data. Then there's a 4th one that you see in the 6th one, sorry, I can't count even. You find the 6th one in the WMAP data, which is almost as strong as those other 5. Look back in the Planck data, it's there too. So I think those 6 spots are very likely genuine Hawking points, and you might see effects in the other data too. I can go into that if people want to, but I think I've run over my time, so I should stop here. Thank you very much.
Thank you very much, Professor Penrose. Have we got any questions from the audience?
I think previously you mentioned you can consider space-time as a topological space.
Sorry, I'm afraid I missed the question.
Sorry.
Can you say a bit louder?
I think in a previous slide you said we can treat space-time as a topological space.
We can
We can treat space-time as a topological space.
topological. Oh, I see.
Oh, yeah.
Yes, I mean, the arguments I used for the black hole singularity theorem were topological type of arguments. But we don't know what the topology of the whole
okay.
universe. It might be, I haven't actually mentioned that in the argument here. It could be something other than trivial topology, like just a sphere or a hyperbolic space or whichever it is. I don't know. I suspect if it was topologically complicated with some identifications, you might see the same effects in different places. So it would be a test. The trouble is, if they're happening at different times, it's not so easy, because the Hawking points, you have to catch the galaxy at the right moment or you don't see it. So I'm not sure. It might be tricky, but you might get some answer about the topology of the universe as a whole, the spatial topology.
I see.
So if that's what you're asking about, yes.
So based on the current evidence, is there more evidence supporting it's topologically closed or topologically open?
More atoms, you say?
Evidence.
No, evidence, sorry. I don't think it gives any evidence for topological structure so far. It's an intriguing question, and I know people try to match patterns in the sky in different places. As far as I'm aware, there is no evidence, no convincing evidence for any topology other than, well, maybe a closed, I mean, people say flat, that's the normal thing people say, because the curvature on the large is pretty small. But I don't think, I would guess it's not flat, but that's just me guessing.
Thank you so much.
Yes.
Eli, could you pass it over to this gentleman? No. This gentleman there?
Test.
Hi, thanks. That was a really interesting and fascinating talk. My question, I was really interested in what you were presenting, your ideas, but there's a slightly different question. But what's your opinion of the many worlds interpretation of quantum mechanics?
Many worlds interpretation. No, I'm not a many worldsist, although I should say in Oxford, the philosophers are very keen on this scheme. I don't know if people are familiar with it. You see, in quantum mechanics, I did mention the issue of the collapse of the wave function, where you have a body in one of my pictures in two places at once, and we don't seem to see that. We see atoms in two places at once, but we don't seem to see macroscopic bodies in two places at once. Now, the view I hold, which I sort of hinted at, is that it's really a gravitational effect, and that you can work out, if you imagine a body in the superposition of two places at once, you do a calculation, which is roughly speaking, imagine two copies of the body on top of each other, pull them apart, and then consider only the gravitational effect, no other force. Then that is a certain energy. That energy is an energy uncertainty inherent in that superposition. And so the argument is that that superposition has a lifetime, which according to the Heisenberg time-energy uncertainty principle, that lifetime is essentially the reciprocal of that energy uncertainty. Now, the trouble is that when one looks at actual superpositions in quantum mechanics, the amount of mass displacement is tiny. And so the lifetimes you're looking at are probably longer than the age, well, I can't say the age of the universe, because the age from the Big Bang to now. So, a long time. So you have to get sufficiently large masses to start to see the effect. There are experiments which have been trying to look for this effect. Nothing so far has seen it. But that's consistent with how much the experiments have been able to achieve so far. I'm hoping that there will be more sophisticated experiments in the not-so-different future. We'll look to see if this gravitational collapse of the wave function, I call it, will take place. And that would say why the many worlds universe doesn't take place. The many worlds universe says all these alternatives happen at once, and for some reason which I could never quite understand, we only perceive one of them at a time. I think it means one's consciousness or something bifurcates or something. I don't quite know what it means. And that whatever conscious being you are, you're only allowed to see one of these branches. It runs into lots of troubles, but the philosophers in Oxford are used to playing with these ideas.
I am super, super excited to see you today. I do have a question about the talk. So according to the talk, the information from the supermassive black hole spread out at the point decoupling D. At G, right?
The information paradox, is that what we're talking about?
Yeah.
Yeah.
So if information only is spread out at there, what happens to smaller black holes in our eons, which they, after Hawking radiation, what happens
Well,
to
the
them?
little ones evaporate sooner because they're hotter and they therefore, they're smaller and they're hotter. It doesn't, well, you see, according to the scheme I have, you will lose information. But you see, I don't mind it losing information because the trouble, I don't know if this is what you're referring to, but people often refer to this as the information paradox. I did have this picture just a couple ones back, I guess it was. That one, yes, which was illustrating, this is the conformal diagram on the right-hand side, and the left-hand side is the picture of what we have. And then you see the singularity, although the wiggly line on the left-hand picture looks as though it's time-like, the cones are all pointing at it, so it's really space-like. So the conformal diagram on the right shows the singularities of that wiggly line, which is horizontal and therefore space-like in the picture. And that means that the little cones, as they point up to it, just run into it. So there's nowhere for the information to go except onto that singularity. So the view I hold is that it is just destroyed. Now, there's no problem about that in the way I think about it, because when you have general relativity combined with quantum mechanics, and this is what I was trying to say, it's got to modify quantum mechanics. And it modifies quantum mechanics in a way that the collapse of the wave function is a gravitational effect. And so the fact that you don't preserve unitarity is part of the scheme. So I think to try and preserve unitarity, this is my point of view, that trying to preserve unitarity in quantum gravity is a mistake. That although this is what people do because they don't want to change quantum mechanics, you're running into trouble already with general relativity for the sort of arguments I rather hastily presented earlier, that you're having a problem with the principle of equivalence in general relativity. Principle of equivalence runs into difficulties with the principle of superposition. And this, in my view, tell us that you do lose information. And also in measurement, one thing happens or another thing happens, not a superposition of the two, and you throw away various things like entanglements with other systems and so on. So but that's maybe hard to, we don't like that idea usually, we don't like to lose information, but you certainly will lose it at the crossover, if not before. You're well below, as it comes over onto the other side, you're way smaller than the Planck scale. So we don't know anything about the physics which goes on there and why information should be preserved. So this is my view. I'm afraid it's not the same as most people's, but still.
Thank you very much.
Yes, thank you. And thanks for reminding us of those ideas of the collapse of the wave function. But my question is a little bit more technical.
I'm sorry, I can't hear it. It's too quiet.
Sorry, my question is a bit more technical perhaps, but you mentioned that at the Big Bang, Weyl curvature was, I believe it was zero, but Ritchie curvature wasn't. And you described briefly the conformal transformations, the conformal transformation that you had to make for your CCC cosmology. And I was wondering if it was necessary to have zero Weyl curvature for the conformal regularization of the Big Bang singularity.
Well, in the normal cosmological models, the Weyl curvature is zero. I sort of missed I'm afraid my hearing is not all that great, so it's not hard. I find it hard to get exactly what your point was. I'm sorry.
I might be also mistaking the Weyl curvature and the Ritchie curvature in what you said, but one of the two, if I remember, you said was zero.
The Weyl curvature should be zero. Well, yes, I didn't say that in the model. Yeah, perhaps I don't know if that's what you mean. But in the model I have, the Weyl curvature is automatically 0 in the Big Bang. Okay, at the Hawking points, it's infinite, but don't worry about that. But most places, almost all places, it is 0. And this was a nice feature because it automatically comes out 0. There are general theorems, particularly theorems due to Helmut Friedrich, which considers what happens in an exponentially expanding universe where you have if the thing is dominated by massless stuff, then the Weyl curvature goes to 0 in the remote future. And so it is 0 in the crossover, which is good because you can do all sorts of calculations which work when it's 0 and they have trouble otherwise. So the Weyl curvature does go to 0 in this picture automatically because most of the crossover from one eon to the next is not at Hawking points. You're at this place where it's smooth, and where it's smooth, the Weyl curvature automatically 0 by the Helmut Friedrich type of argument, and so it becomes 0 in the next eon, automatically. Does that answer your question?
Yes, somewhat. Thank you.
The only places it's not 0 are at the Hawking points, and there it's infinite. So it's a singularity basically there. But it has a singularity where you can calculate it's got an energy which comes through onto the other side, and so you can't get rid of that.
I'm afraid we've only got time for one more question.
Hello. You presented this very nice argument on how supermassive black holes might lead to these Hawking points. Is this generalizable to any kind of singularity, or just these specific black hole ones? Because you mentioned all these other possible singularities, even naked singularities that
You're
are
talking
technically
about
allowed.
a duality.
So would other singularities, such as the naked singularities you mentioned, also lead to the same conclusion of a Hawking's point?
It doesn't tell you much about the Hawking points because, well, the places, as I think I mentioned a moment ago, on the next eon, the size of those points, compared to if you're just looking at how much the radiation spreads, is squashed into far smaller than the Planck scale. So if you're talking about ordinary physics on that side, you haven't the remotest idea what's going on. So I haven't the remotest idea what's going on. But what you can say, through general theorems, you can say how much mass there is, which is an interesting... Christoph Meisner and I are working on a paper which is to explain that point. You see, since the crossover is mostly smooth, and you can do your calculations where it's smooth, you can't do it at the Hawking point because things blow up. It's a singularity. But you can work out what the mass is by doing integral at the place where it's smooth. And that integral carries through from one side to the next. And so therefore, you can tell how much mass there was which produced that Hawking point from the observational intensity of the spot that you see on the other side. With that is a paper which is in progress at the moment. And I hope we'll have the details of that before too long.
Thank you.
I'm conscious of the fact that I need to get Professor Penrose back home. So I want to thank you for a very thought-provoking and inspirational talk, and thank you very much for coming to King's. We're really proud for our association with you, and very grateful that you were able to come today and talk to us. So let's thank Professor Sir Roger Penrose again.